here. So it says, first of all, let's say you have a curve C and it's smooth, all right? It's a smooth curve. So we can't do any crazy-ass curves. It has to be, there's a way that you could do curves that this would all fall apart. But if you got generally a smooth curve, then does anyone remember the definition of smooth? It's way back, chapter 10. Something about a derivative as well. You can go back and look in chapter 10. For us, it doesn't have any cusps, okay? The curve can't have a cusp in it, all right? I'm talking about a curve in 2 or 3 dimensional space. So as long as you got a smooth curve, and that curve is given by some vector function, where that vector function is restricted, right, between A and B, that draws my curve. And as long as f, little f, is a differentiable function of 2 or 3 variables, such that the gradient of that scalar function is continuous on that curve. So basically, this is just saying that we need all these things to behave well, right? No crazy exceptions that some mathematician could come up with that would be like, see, this doesn't work, because there's always exceptions. So we have to have some conditions. So as long as we've got some reasonable functions, then we have the following. The gradient, if you take the line integral of the gradient of f, now what's the gradient of f? Is it a scalar function, vector function, constant? What is it?
It's a partial.
You do the partials to get it, but what do you get at the end? When you do a gradient of a scalar function, you get a what? A vector, right? So if we take the gradient of some scalar function and we dot it with, that really means the magnitude, or sorry, not the magnitude, well it does, but that's for us is r prime of t, right? R prime of t. Then dt. Then instead of doing all that, right, calculating all that, instead all you have to do is take f, the scalar function, and evaluate it where? At the 2 endpoints of the curve. So you see how here we have capital F and little f? For us, this is like the capital F, and then what would the derivative of that be? The gradient is the derivative of that f. So this is kind of like little f, capital F, because that's a gradient. I guess you could do it this way as well. Come back over here and replace this little f with capital F prime. Isn't that the same as little f? We're saying this is the derivative of that, right? So that's what's happening here. We have f here. That's the derivative of f. It's the gradient is the derivative. All right, so we have this theorem says the line integral of a conservative vector field. What the hell are they talking about? What's a conservative vector field? It's a vector field that comes from the gradient of a scalar function. So I defined this 13.1. Said, hey, if somebody hands you a scalar function and tells you to find the gradient, that vector field you get, that vector function, right, is conservative because it came from a scalar function. That's the definition of conservative. So obviously that comes from, that's the gradient of a scalar function, right? So that's conservative. So this theorem is saying that as long as this is a conservative vector field, which it is, right, then this answer will simply be the difference of the value of the function at the 2 endpoints of the curve. Further, the line integral of any 2 paths that connect the same 2 endpoints are always equal if f is conservative. This is a big note right here. Because the way you can look at it is, as long as this f is conservative, then if, let's say I give you some curve that looks like this, C, right? That's the first endpoint, right? Let's call this R of A, and let's call this R of B, right? Those are the 2 endpoints of the curve. The answer, right? The answer to this should just be the f evaluated at those 2 endpoints. As long as this is a conservative vector field, then the curve I draw is irrelevant as long as it starts here and ends there. Why? Because the answer should be just the evaluating at the 2 endpoints. So the path does not matter as long as that's a conservative vector field. That make sense to you? Doesn't matter how I get from here to here. this integral, the work integral, will be the same. So on Earth, right, and I'm getting ahead of myself here, when you're calculating work on Earth, is gravity a conservative vector field? Have y'all learned whether or not our gravitational field is conservative or not? No? We'll leave it as an open question. Because if gravity is if our gravitational field is conservative, then the work done from me getting from here to the projector does not matter how I get to the projector. It means I can go from here straight line or I can go around like that. The work would be the same. Now, let's leave it as an open question. But for conservative vector fields, the path doesn't matter. So we call this path independence. So let's do an example so we can see this kind of in action, I guess. So I give you a scalar function, right? And we're asked to find this, right? Now, let's act like we don't pay attention in Cal 3 class. And let's act like we are just going to grind this out and like we didn't just see the previous theorem, all right? Then I'm going to compute this. So I need to find this, right? First, what's the gradient of f? You just can take the partials of this. What's partial of that with respect to x? 2x, comma, 2y. Do y'all agree that that's my two-dimensional gradient vector field? Okay. I need to take that dot dr. So I need the curve. Okay, there's my, oh wow, it was given to me. R of t, right, is t sine t, t cosine t. My t is restricted between 0 and pi. I'm going to need r prime, aren't I? In the formula, this right here, right, means I'm going to need r prime. Keep in mind, this right here is what our capital F was in the previous examples. This is our field. But it just came from the gradient, right? It came by taking the gradient of some scalar function. So I need the derivative using the formula that I erased that was on the board here. Oh shit, I don't like this derivative, but oh well. Right, derivative of each one, I have to do a little product rule here. Okay, sine t plus t cosine t. And then this one would be cosine t minus t sine t, right? Because you'll get a negative when you do the derivative of the cosine. Okay, there's your derivative. So now I'm going to do this. This will be the integral from 0 to pi. Okay, I need the field evaluated on the curve, right? The field evaluated on the curve dotted with the derivative of the curve, dt. That's what I'm doing right now. So what is our field on the curve? So 2 times x, but what's x? For us, it's this, right? So the vector 2, what? T sine t. And then this 2y would be 2 times that y coordinate, which is 2t cosine t. Take that vector, dot it with the derivative. Ah, crap. Sine t plus t cosine t, cosine t minus t sine t dt. Now I have to do a dot product. Equals integral 0 to pi. All right, when I multiply these together, right? Let's hit this one first. I get 2t sine squared t. Oh my. Then I have to hit this one. So plus 2t squared sine t cosine t. Okay, that's the first part. And then I got to do this one with this one. So plus 2t cosine squared t. I'm kind of happy to see that. And then this one, oh wait, hold on. Minus 2t squared cosine t sine t. I think some things are going to cancel and become nice. Those are gone, right? That's good news. And then these are both, what, 2t cosine squared t, 2t sine squared t. Factor out a 2t from both of those. And then Pythagorean identity would turn into 1. Can I just go right to 2t here? This is actually not that bad, is it? Integral 0 to pi of 2t dt. The antiderivative of 2t dt is t squared. Evaluate 0 to pi. Pi squared. Pi squared. Pi squared. I would say that wasn't terrible, right? That wasn't terrible. But I didn't use the theorem. The theorem says that if you're trying to evaluate the line integral along the curve C of some vector field dr, if this vector field is conservative, then you don't have to do all this. All you have to do is evaluate the scalar function at the two endpoints of the curve. And that's all you have to do. So now I'm going to act like I did pay attention in class, all right? And what I'm going to do is this. I'm going to say fundamental theorem of line integrals. I'm going to use this. Obviously, our field is conservative because it is the gradient of some scalar function. So all I need to do is find the two endpoints. What's A for us in this problem? What's A? 0. And what's B? Pi. All right? Let's do these. I'll do them in that order. What's R of A? For us, that's R of 0. What do you get when you plug 0 into our what? R. Our position, right? Our position. Plug that in, and we're going to get a vector, aren't we? 0, 0. Okay, now plug in B. B is 1 pi. 1 pi. Pi. Right? What happens when we plug in pi? Sine of pi? 0, right? So 0, and then cosine of pi? Negative 1 times t, well, which is pi, so negative pi. Is that okay? Those are the two endpoints of my, my vector function, my curve, right? So now instead of doing all that, what I'm going to do is use the fundamental theorem of line integrals, right? Fundamental theorem of line integrals. And I'm going to say, okay, this is just equal to f evaluated at r of b minus f evaluated at r of a. Now for us, that means f evaluated what? At 0, negative pi, and then minus f evaluated at, let me write it this way, 0, 0. I should have done, and I told you about what this notation means. It's a weird notation, but I explained this to you when I first showed it to you, that what this notation means, to plug a vector into a scalar function, just means you replace that with x, that with y. That with x, that with y. So let's plug that into our scalar function. I'm saying into this, right? So what would I get if I plug 0 in for x and negative pi in for y? I get pi squared. And then what would happen if I plug in 0 for x and 0 for y? You get 0. And your answer is pi squared. That's it. We're done. That's just to show you get the same answer, right? So obviously, on your final exam, right, if you're given a problem like this, you might be wasting your time if you don't use the fundamental theorem of line integrals, right? Because just finding the two endpoints is pretty straightforward, and then plugging them in is pretty straightforward. All right, can I go on? If we're trying to compute this line integral along some curve over some vector field, if that vector field's conservative, all we need to do is evaluate the scalar function at the two endpoints. All right, path independence. A theorem. First, that's a closed curve. Any curve that starts and ends at the same point is conservative. Is closed, right? You start and end. So we have a same initial point and same terminal point. All right. Is this obvious then to you, this next statement? So what if I tell you that every time you try and compute this line integral, right, over this vector field, along any curve, doesn't matter what curve you ever pick, you pick any curve you want, and I tell you the answer is 0, right? Sorry, the curve doesn't matter. For every closed curve. So I'm sitting here in space, I pick some curve C, it starts here, it ends there. Let's call that C. Pick some other C, it starts here, ends here. Call that C1, C2. Start here, go like this, come back. Don't want to cross over ourselves. Let's keep it a simple curve like that. Okay, that's C3. What if I tell you for every curve you ever pick, you always get 0 as an answer? Well, that would mean that that field must be what? If you're always getting 0, that means it's like you're taking the value at the two endpoints and subtracting, and they're the same value, right? So you're getting 0 every time. And that would mean that your field is conservative, which means that you're path independent, which means that no matter what path you take, you're always going to get 0, as long as it's closed. So this theorem is actually, it's good, but it's not what we really need. Okay, what we really need, let me see here, is this right here. This part right here is really the part we want to take away. Remember that when we say that that's conservative, right? When we give you a field that's conservative, we know then that we just have to subtract the two endpoints, right? If it's conservative vector field, we know we can subtract the endpoints. But now if I give you any closed path, then we know that the two endpoints are the same. And that way, when we do this, these two subtract to be 0 every single time. Every single time. So the value of the line integral, right? If you have a conservative vector field, the value of the line integral on any closed curve should be 0. All right, so how do we determine if a field is conservative? That's what we need to do now. Determining if f is conservative. Now, the previous problem, I gave you little f, didn't I? The scalar function, and we took its gradient. And by definition, that meant our field was conservative. But if I just hand you a field, how do you know it's conservative or not, right? That's what we want to do. So first, we have this idea of what's called a simply connected region and a not simply connected region. And this actually gets into a topic in math that we're not going to get into, but I can kind of explain it to you, maybe. Imagine the idea of simply connected means if I'm standing here, let's say I'm standing in this little space, and I have a lasso, okay? I have a lasso. And I throw that lasso out into space, right? And then I start reeling it in. I never get hung up on anything. No matter where I am, if I throw my lasso out here and then I reel it back in, I'll never get stuck on anything. That's called the simply connected region. This actually has to do with what's called topology, all right? This here doesn't work. If I'm standing here and I throw out a lasso, if I throw that lasso out, then yes, I can reel that in. But if I throw a lasso out that goes like that, then you look at that little island there as kind of stopping you from pulling your lasso completely back in. So that is not a simply connected space. Another way is to think like if you just have like a rubber band, take any rubber band you want, draw any rubber band you want in here, imagine shrinking it down to a point. Do you ever go outside of that region? No, you're always within that region. But if I draw this one, right? Try and shrink that one down to a point, and what happens? you're gonna have to go through this empty hole, right? So not simply connected, simply connected. So now we establish the conditions for F to be conservative. So if somebody gives you a vector field, right, we're now going to have a very simple way of checking to see if a vector field is conservative. Let's say someone gives you a two-dimensional vector field, two-dimensional only. This does not work for three-dimensional. Two-dimensional vector field. So let that vector field be defined on some simply connected region. So again, as long as your region isn't crazy, this is going to work. So suppose P and Q have continuous first partial order derivatives. That just means that we can take the partial derivatives of these. Then if we can, here's the check to see if something is conservative. What you're going to do is you're going to take the partial derivative of P with respect to Y and take the partial derivative of Q with respect to X and see if they're the same. If they are, then it's conservative. Now, right now, this is not going to make sense why. All right? Later on, we're going to have something that we do when we get to a vector field that's three-dimensional. And when we get to that later, I will show you where this comes from. For now, can you just take that on faith? Yeah, is that all right with you? All right, so look, this theorem is actually really simple to use. Let me put it over here. So for conservative, we need, if F is some field given to us, I'm going to write PQ instead of P of xy, Q of xy. It's just some function, PQ. Then F is conservative if partial P with respect to y equals partial Q with respect to x, right? That's what we have to check. So look at this. Tell me if this is conservative or not. Well, this is P, right? This is Q. It's a two-dimensional vector field. Is it conservative? Well, let's do it. What's partial P with respect to y? 2x. What's the partial of Q with respect to x? 2x. Is that a conservative vector field? Yes. It is. Yes, it is. That means that if I were to take some curve, right? Let's say I have a curve that starts here, goes here, and comes back to that point, and I call that C. Then any line integral I do along that curve through this vector field, the answer would be what? 0. Because that's a closed curve, right? So the starting and ending point would be the same. That means all I have to do is subtract the value of the scalar function of the two endpoints. But those two endpoints are the same, and so you should always get 0, right? So this is just recalling a definition. Let me get to this. I just want to do this example. All right, first of all, look at that function, that field. That's a different field, right? Is it conservative? Quick check. What's P? P is this one, right? That's P. This is Q. All right, we do the partial P with respect to Y. What's that? That's not the same problem, right? We're getting the same answers here, but it's not the same problem. And then 2x, right? Is it conservative? Yes. Okay. But now I'm asking you something I did not ask you on the previous problem, and that is what? Find its potential function. What the hell is potential? I skipped the definition. I skipped it. I just scrolled through it real quick because I want to explain it in this example. The potential function is the scalar function that you take the gradient of to get that, right? This is conservative, which means, being conservative means there exists some scalar function, in this case f of xy, whose gradient is f, right? There's some scalar function that when I take the gradient of that, I get that. Find it. Find the scalar function that when you take its gradient, you get that. Understand what I have to do? Yeah, so we need to do something that's going to require some partial integration is what we're going to call it. I just want to make sure everyone understands what we're trying to do. Trying to find some scalar function f that when I take its gradient, I get that. Okay, so here, let's write down what we know. All right, here's what we know. We know f is conservative, right? F conservative means that f is the gradient of some scalar function. We just don't know what it is, right? And I know that the gradient of a scalar function, in this case because it's two-dimensional, should be the partial of that f with respect to x, partial of f with respect to y, right? So what we're saying is that that field up there is this, right? And that means for us that this is what? 1 plus 2xy plus natural log x. And then the partial of f with respect to y is just x squared, right? So I'm now going to use that information. I'm going to use that information. And here's how I'm going to use it. So this means that the partial of f with respect to x is 1 plus 2xy plus natural log x, right? I'm just saying that that must be that, right? We are looking for little f, right? Little f. We're not looking for the partial of little f with respect to x. We know what that is. We want what little f is. So this is what I got when I took the derivative of f, right? This f. I know that when I take whatever this is, when I took its partial with respect to x, I got this. Let's reverse the process. How would you undo that? Integrate, right? So I'm going to do the integral on both sides. I'm going to do the antiderivative of f, the partial of f with respect to x, with respect to what? X, right? I'm undoing this by taking the antiderivative of it with respect to x. Why with respect to x? Because that's the partial with respect to x. So I'm trying to undo that. What I do to one side, I must do to the other. I'm taking the antiderivative of that with respect to x. Now, you have to be real careful with this. This gets a little bit tricky. This side should just be little f. This should just be little f. This side here, what would the antiderivative of 1 be with respect to x? So what do you take the derivative of to get 1? X. Okay, that's x. Plus, okay, here you treat the y like a constant, right? The 2 is a constant. Antiderivative of x would be 1/2 x squared. So this just becomes what? X squared y. So far okay? Plus, oh shit. What's the antiderivative of natural log of x? It's not 1 over x, that's the derivative. Yeah, this is one that hopefully you've got memorized by now. It's x ln x minus x. That's the antiderivative of this. It's these two. Okay? Plus, normally we would say here plus what? A constant, right? Because anytime we do an indefinite integral, we're always off by some constant, right? But here we can't say constant because whatever f was could have had some stuff over here that had just y's in it, right? Just y's, no x's at all. Could have been like sine of y. And then what would the derivative have been of that with respect to x? 0, right? So I'm not saying that this is just a constant. I'm saying that potentially this is something with y's in it. So I'm going to just put g of y. Some function of y potentially, right? Now it could turn out that it's just a constant. But I need to account for the fact that it might have some y's in it. That okay? All right, now, What I'm going to do next, I'm going to leave that right there. What I'm going to do next is just kind of clever. It's not me being clever. I'm never clever. I'm just following the lead of other people, right? Now, sometimes I'm clever. I take that back. What I'm going to do is I'm going to take this, and I know it a little bit, right? I know kind of what it is. I'm off by a function of y. I'm going to differentiate this with respect to y. And when I do that, I should get this, right? So let's take this answer, let's differentiate that with respect to y, see what we get. 0 x squared. By the way, these x's could have canceled. I don't know if you'll see that. You'll see the x's could have canceled? Yeah. It's all right, they're going to go away anyway. Okay, so that, and then what's derivative of this with respect to y? 0, 0, and then plus y prime. I'm going to put g prime of y. It's the derivative of y of g with, right? Now you could also, this notation is actually not that good. Because does this tell me what I'm differentiating with respect to? It doesn't. What would be a better notation than this? G subscript y. That would be like a derivative of g with respect to y. Because I'm differentiating with respect to y here, right? So I'm going to change that notation. You could use it, but I'm going to change it to this. G subscript y. I'm taking the derivative of g with respect to y. All right. Let me back up real quick. We said, hey, we know what this is, right? We know what this is. That's what it is. We integrated with respect to x, and that allowed us to find f within some function of y. Now we're going to be clever, differentiate that with respect to y, and we get this. And what do we know that this must be? This must be this, right? Right? Because that's what they were given. They told us the partial with respect to y, partial of f with respect to y had to be x squared. So what does that tell you the partial of g with respect to y is? 0. Sorry, that's going to be loud on the camera. Oh well. So this right here means that using these two things together, right, means that partial of g with respect to y must be 0, right? So I need to know what g of y is, right? I need to know what g of y is. And all I can tell you is this. If I integrate both sides, take this. If I integrate both sides with respect to what? Y. The antiderivative of the partial of g with respect to y should just give me what? G of y. And that must be equal to the antiderivative of 0, which is a constant. C. So guess what? This is some constant. It has to be a constant. Any constant. So my final answer now is this. I'm ready for my answer. My final answer